In this lesson, we will look at the other components, which along with the air conditioning packs, make up an aircraft's air conditioning system. We will then examine how the air temperature is controlled and how the air is distributed throughout the aircraft. We will finish off by having a quick look at a vapor cycle air conditioning unit. When operating on the ground or at low altitude, the charge air entering the air conditioning pack may be very humid. When the air is cooled, this humidity will condense out as water droplets. In order to prevent it raining on the passengers and crew, a water separator is fitted in the pack downstream of the turbine of the air cycle machine. The water separator consists of two parts, a coalescer and a series of collector tubes. When the air leaves the air cycle machine, the water will be in very small droplets, in the form of a fine mist. The purpose of the coalescer is to increase the size of the water droplets. It consists of a filter, normally of coarse wire gauze. The water droplets come together on the gauze, forming larger drops before they are carried through to the second stage, where a swirl is imparted into the air. The centrifugal force throws the water drops outward. When they strike the collector tubes, they run down to the bottom of the case and exit via the water drain. The relief valve will open to safeguard the airflow to the cabin should the coalescer become blocked with ice or debris. The water separator does most of its work in low-altitude, humid conditions. However, at the high cruising altitudes used by modern transport aircraft, the air is very dry. When operating at high altitudes for long periods of time, it may be necessary to increase the moisture content of the conditioned air from the 1 to 2% relative humidity of the ambient air to a more comfortable level. The component used to do this is the humidifier, a typical example of which is shown here. The water tank contains drinking water. It is pressurized by bleed air from the engines. This tank is usually referred to as the potable water tank. The water jet is fitted in a venturi tube downstream of the water separator in the conditioned air duct. Bleed air is also fed into the jet. This and the reduced static pressure of the dry air caused by the venturi effect ensure that the spray of water mist is absorbed into the air. The fabric-covered swirl vanes further ensure that the air and moisture are thoroughly mixed. The fabric absorbs any extra moisture, giving it back when the humidifier is switched off. The water supply valve is controlled by a humidistat. This is a device which can measure humidity and operate a switch when a particular level is reached. It is measuring the humidity in the air conditioning duct. When the humidity falls below a predetermined level, the valve will open, and humidification will commence. The pack flow control valve may incorporate a mass flow controller, or it may be a separate unit. The mass flow controller is fitted to ensure that a constant mass flow of air is supplied to the air conditioning packs, regardless of the engine RPM or intake air pressure. This helps to make control of the aircraft pressurization much easier. When used with blower systems, the mass flow controller operates a spill valve, which dumps excess air to atmosphere. In systems that use engine bleed air, the mass flow controller adjusts the airflow through itself, so that the required mass flow passes to the system irrespective of changes in the value of the pressure upstream and downstream of the unit. The simplified mass flow controller shown here consists of a piston with cutouts in its face and barrel, which moves inside a cylinder with matching cutouts in its barrel. When the inlet pressure is low, the spring will push the piston fully to the left, and the cutouts in the barrels will be fully aligned, allowing maximum airflow through the unit. As the inlet pressure increases, the mass flow will tend to increase. However, the increased pressure on the face of the piston will move it to the right against the spring, reducing the airflow through the unit. Thus, with pressure changes, the piston position will modulate in the cylinder, maintaining a constant mass flow to the packs. Control of the pack outlet temperature is usually achieved by mixing hot air with the cooled air from the air cycle machine. The temperature control can be either manual or automatic. Automatic temperature control is achieved by comparing a pilot-selected temperature with the actual temperature of the air. In your aircraft, you will find that the selector does not have temperatures marked on it, but merely hot and cool. However, to aid understanding, we will mark our selector with temperatures. The temperature of a sensor in the cabin is compared electronically with the selected value, and any difference modulates the hot air valve to allow more or less hot air to bypass the cooling components to increase or decrease the cabin temperature. If, for instance, the pilot selects an increase in temperature, the hot air valve will open to warm up the cabin. Once the selected temperature is reached, the valve will modulate as required to maintain it. If the manual auto switch is moved to the manual position, the hot air valve will now move in direct response to the temperature selector switch position and remain in the selected position. The pilot is now no longer selecting a temperature. Instead, he is selecting the amount of hot air to be added. The cabin temperature achieved will vary with the environmental conditions. In order to avoid large temperature gradients between the extremities of the cabin, it is often necessary to divide the cabin into zones and control the temperature in each zone individually. This control is achieved from the flight deck using zone control knobs or switches. The larger the aircraft, the more zones there will be. The Boeing 747 has 5 zones, whereas the Airbus A320 has 3. The temperature of the air delivered by the packs is determined by the zone requiring the coolest air input. This will normally, but not always, be the flight deck. Individual zone requirements are satisfied by adding hot trim air from the bleed air system to the output of the air conditioning packs. The amount of trim air added is controlled by zone trim air valves. Their positions are dependent on inputs from the individual zone temperature control systems. The trim valve for the zone requiring the coolest air will be closed. The hot air pressure regulating valve modulates to control the pressure of the trim air. If required, this valve can be closed by a switch on the control panel. Most passenger transport aircraft supply warm air to the cabin by means of floor and wall passages, and this warm air maintains the interior surfaces at cabin temperature, reducing drafts and direct heat losses, which in turn allows the entering air temperature to be closer to the cabin temperature. Recirculation fans are used to augment the air conditioning packs, allowing a reduced number of packs to be used during the cruise, which decreases engine bleed requirements and improves fuel economy, while still maintaining a constant ventilation rate throughout the cabin. The fans draw cabin air from the underfloor area through filters, then reintroduce the air into the conditioned distribution system. Air from the areas around the toilets and galleys is not recirculated, but is vented directly overboard. The ducting is in 2 distinct sections, to provide for separate flows of cold and heated air. The cold conditioned air is supplied to the passengers individually, through a system known as the Gasper air system. Gasper air is tapped from one of the zone's supply ducts upstream of where trim air is added. The Gasper fan provides a positive supply of conditioned air to all zones through individually controlled outlets or punker louvers. Conditioned air is supplied to the flight deck crew stations, where it can be adjusted for flow direction and quantity. It is also supplied to the flight deck windows for demisting purposes. The flight deck crew is able to monitor both the cabin and the duct temperatures throughout the aircraft. On the Airbus electronic screen air conditioning page, shown here, the zone temperatures are shown, as are the duct temperatures. The positions of the zone trim air valves are also graphically displayed. The crew also receives warnings in the event of malfunctions in the system. For instance, if the temperature of the air in the trim air duct becomes excessive, the amber fault light in the switch will illuminate. The vapor cycle air conditioning system is similar in operation to the domestic refrigerator, or the galley cart cooling system used on some large aircraft. Its use for aircraft is now generally limited to small piston engine types. The system uses a refrigerant, normally Freon, which alternates between the vapor and liquid states. It is compressed, cooled, expanded, and heated in that order. The refrigerant is a liquid which boils at approximately 3.5 degrees Celsius at sea level atmospheric pressure. At higher pressures, the boiling point is increased, and vice versa. The major components of the system are the evaporator, the compressor, the condenser, the expansion valve, the receiver, and the electrically driven blowers which pull outside air into the aircraft across the evaporator. The system operates on a continuous cycle, but in order to explain the system more clearly, we will look at a unit of Freon as it makes its way around the system. The receiver, which acts as a reservoir, contains high-pressure liquid Freon. On leaving the receiver, the Freon comes to the expansion valve. This valve allows the Freon to expand, reducing both its pressure and temperature as it enters the evaporator. As the Freon passes through the evaporator, it takes heat from the cabin air, therefore cooling the cabin air. As the temperature of the Freon increases, it boils, changing from a liquid to a low-pressure vapor. The compressor raises the pressure and the temperature of the vapor before it enters the condenser. The condenser is positioned so that cold ram air passes over it. This causes the vapor to give up its heat, causing it to condense back into a high-pressure liquid. The pressurized liquid then passes to the receiver, ready to begin the cycle again. That is the end of the lesson. You should now know that air conditioning systems may have a centrifugal water separator for use at low altitude, and a humidifier supplied with potable water for use at high altitude. You have seen that the mass flow controller ensures that the air conditioning packs receive a constant mass flow of air throughout their operating envelope. You should know that the cabin is split into a number of zones, and that the outlet temperature of all packs is set by the zone requiring the most cooling. Zone trim valves add hot air to the other zones to satisfy their requirements. Recirculation fans are used to augment the air conditioning packs. And the Gasper system supplies cool air to individual seats. Finally, you should have learned that on some smaller aircraft, a vapor cycle air conditioning system is used.